Welcome to this explainer. We're jumping right in today, taking a close look at the invisible molecules that quite literally build the world around us. We're tracking the polymer revolution, from historical, world-changing crises all the way to cutting-edge 3D printing.
So, to get things started, let me throw a slightly weird question your way. What do an old-school set of billiard balls, the crinkly shrink wrap on that package you just got delivered, and a life-saving artificial heart all have in common? Honestly, on the surface, not a single thing. But zoom into the molecular level, and it turns out they're all revolutionary polymer products. To really wrap our heads around how we got here, we've got to rewind a bit to the early 1900s. Back then, playing billiards was huge, but there was a massive bottleneck. The really high-quality billiard balls were carved straight out of elephant ivory. Obviously, that led to a huge ivory shortage and sparked some serious early conservation panic. But then, along comes this brilliant chemist named Leo Bakelite. He cooks up a synthetic material called phenol formaldehyde, which you probably know as Bakelite. It was actually one of the very first synthetic polymers, and has swooped in and totally solved the billiard ball crisis. I absolutely love this little detail from the historical records. It notes that the elastic characteristics of this polymer are very similar to those of ivory, and when phenolic billiard balls collide, they make the same clicking sound as ivory balls. I mean, how cool is that? It perfectly highlights that from day one, polymers weren't just seen as, cheap plastics. They've always been these world-altering synthetic materials with incredibly tailored, highly specific properties. Okay, so here's our game plan for this explainer. Number 1, mechanics, stress, and silly putty. Number 2, heat, melting, and glass. Number 3, plastics, elastomers, and biomaterials. And finally, number 4, shaping polymers and 3D printing. Let's dive right in.
Section 1, mechanics, stress, and silly putty. So how do these massive, complex molecular chains actually hold up when we push them to their physical limits?
When you put them under a physical stress, polymers basically fall into 3 distinct camps. You've got brittle polymers, which stubbornly resist until they just violently snap and fracture. Then there are plastic polymers. These guys resist elastically at first, but push them hard enough and they permanently yield and deform. And elastomers? Well, they're the fun ones. They undergo massive stretching, but then bounce right back to their original shape. Let's zoom in on that second group for a second, the plastic ones. When a semi-crystalline polymer permanently deforms, it doesn't just happen all at once. It's a highly orchestrated microscopic process. First off, the loose, messy chains, called amorphous tie chains, that sit between the structured areas, well, they stretch out. Next, the folded, neat crystalline regions, which we call lamellae, actually tilt toward the direction you're pulling them. After that, those crystalline blocks start to break apart. And finally, in a stage known as drawing, all those blocks and tie chains line up perfectly in the direction of the stress. And here's the wild part. That precise alignment actually makes the material way stronger in that direction. But honestly, here is where polymer physics gets super fun. Think about the last time you played with silly putty. If you roll it up into a ball and chuck it at the floor, it bounces right back, like a solid piece of rubber, right? But if you just hold it in your hands and pull it apart really slowly, it oozes and flows, almost like a thick liquid. This split personality is something called viscoelasticity. It basically means the material's behavior entirely depends on how fast you're deforming it. The rate of strain literally changes everything.
Now, what about those super stretchy, highly elastic materials? Well, in its natural state, unvulcanized rubber is actually pretty soft, kind of sticky, and weak. So, to make it rugged enough for something heavy-duty like a car tire, we use a process called vulcanization. It's a non-reversible chemical reaction where sulfur compounds are mixed right into the rubber. That sulfur acts like a bridge builder, creating permanent chemical crosslinks between the polymer chains. It completely locks the structure together and bam, you've massively increased its elasticity and durability. Moving on to Section 2, heat, melting, and glass. We've seen what physical force does. Now let's turn up the heat. Adding heat actually exposes a massive divide in the polymer world. It's the battle of thermoplastics versus thermosetting polymers. Thermoplastics are kind of like wax. Their molecular chains aren't permanently locked together, which means you can melt them, shape them, and recycle them over and over again. Thermosets, on the other hand, like our old friend Bakelite, form permanent chemical crosslinks when they're made. Once they set, that's it. They will never melt again. They just stay completely rigid until they're literally burned. So when scientists are engineering these materials for heat, they are laser-focused on 2 critical thresholds. First is the melting temperature, or TM.
This is the point where highly ordered crystalline structures just collapse into viscous, runny liquids. But for the messy, disorganized, amorphous parts of a polymer, we have to watch the glass transition temperature, or TG. Below this TG line, the material is basically rigid, brittle glass. But once you cross that threshold, thermal energy kicks in and turns the whole thing flexible and rubbery.
All right, on to Section 3, Plastics, Elastomers, and Biomaterials. Let's look at how all this science actually shows up in the real world. When you step back, the sheer diversity of everyday polymer applications is just staggering. Depending entirely on the chemical structure, the molecular weight, and how those chains are processed, one single class of material can do wildly different things. It might end up as a rigid gear inside a machine, a stretchy thread woven into your shirt, the slick protective coating on your frying pan, the sticky adhesive on a postage stamp, or even the cushy shock-absorbing foam inside your running shoes. Let's check out a super specialized example. Liquid crystal polymers, or LCPs. Normal amorphous polymers are just totally random when you melt them down into a liquid. But LCPs, they are made of these rigid, rod-shaped molecules that stubbornly stay perfectly ordered, even in a liquid state. So why should you care? Well, if you apply just a tiny electric voltage to these LCPs, it instantly disrupts that perfect alignment and blocks light from passing through. And that is the exact magic trick powering the liquid crystal displays, the LCDs, in your smartwatch, your flat-screen TV, and probably the monitor you're staring at right now. Now take a look at this massive number, 4 million grams per mole. That is the jaw-dropping molecular weight of something called ultra-high molecular weight polyethylene. Because its molecular chains are so incredibly ridiculously long, they tangle up like crazy. This creates a material with unbelievable impact strength and practically zero friction. I mean, it's so incredibly tough. They use it in bulletproof vests, and it's so smooth and wear-resistant, it's actually used as the load-bearing surface in artificial hip joints. And that brings us to an absolutely crucial point. Polymers aren't just for consumer goods and electronics. They are incredibly vital biomaterials. Because their carbon-based structures are chemically and mechanically so similar to our own body tissues, they happen to be uniquely biocompatible. Think about it. PMMA is literally used as bone cement. Expanded PTFE is used to graft and repair human blood vessels. We use silicones for flexible joint implants and polypropylene for surgical sutures that won't degrade in the body. They are quite literally saving and improving human lives every single day. Which brings us to our grand finale, Section 4, Shaping Polymers and 3D Printing. Let's talk manufacturing wonders. Traditionally, shaping all these plastics relies on a simple combo: heat and heavy pressure. You've got injection molding, which is the absolute powerhouse for making things fast. They literally ram molten plastic into a closed metal mold to instantly pop out complex shapes. Then there's extrusion, which basically forces molten plastic through a die to make continuous, never-ending shapes like pipes or tubing. And blow molding? That's where you extrude a warm tube of plastic into a mold and blast it with air. It inflates exactly like a balloon against the walls to make hollow things, like your everyday water bottles.
But right now, we are living smack in the middle of an additive manufacturing revolution. 3D printing is completely rewriting the rules for entry-level engineering and rapid prototyping. And guess what? Because polymers have relatively low melting points and can be chemically cured with just light, they are the absolute perfect gold star candidates for these 3D printing technologies.
The two most popular methods out there basically pit mechanical heat against super precise chemistry. First, you have fused deposition modeling, or FDM. You can think of this as a robotic hot glue gun. It just melts and squirts out tiny strings of thermoplastic, stacking them up layer by layer. On the flip side, stereolithography, or SLA, takes a totally different route. It uses a precise UV laser to trace a pattern onto a vat of liquid photosensitive resin. Wherever that laser hits, the resin chemically cross-links and cures into solid plastic, layer by microscopic layer.
But if you want to talk about the absolute bleeding edge right now, we have to talk about a process called CLIP, Continuous Liquid Interface Production. Instead of pausing to painstakingly print one layer at a time, CLIP projects a continuous sequence of UV images through an oxygen-permeable window at the very bottom of a resin vat. Now that oxygen creates a microscopic dead zone that completely stops the resin from sticking to the window. The result? A solid, fully formed object is continuously and rapidly pulled upward directly out of a pool of liquid. It's shockingly fast, and honestly, watching it happen looks like pure science fiction. So think about this. We started our journey a century ago, trying to save elephants by replacing ivory billiard balls with Bakelite. And today,
Today, we are literally pulling completely custom, life-saving artificial organs out of vats of liquid resin. The polymer revolution hasn't just changed things, it has entirely reshaped our civilization. The only question left is, what will the next era of material science unlock? Thanks so much for joining me on this explainer. Keep that curiosity alive, and I'll see you next time.